Welcome to the presentation of our paper dealing with the influence of layered parasitics on EMI improved folded cascode amplifier input stages using compensation methods. Within the scope of this work, we compare three EMI improved differential input pair structures using the concept of compensation in terms of their susceptibility to electromagnetic interference. We pay special attention to the differences in the behavior of the structures at the design stage and the layered stage, to find out if layered specific parasitics can affect circuit performance.
Today, a large number of integrated circuits is used in many electronic systems. Due to the ever-increasing integration density, modern ICs often contain millions of transistors combined in many different function blocks on a single microchip. Sensitive analog circuit blocks and sensors with corresponding sensor interfaces are often integrated with digital function blocks and power electronic systems. When such highly integrated ICs are used in safety-critical applications, such as automotive or industrial applications, their robustness against electromagnetic interference, EMI, is very important. In order to ensure safe operation and not to be influenced in their function, it is very important that the ICs used in these electronic systems are able to reliably withstand a high level of EMI that couples into their pins. Operational amplifiers in particular, which are frequently used as sensor interfaces, often have a direct connection of their inputs to printed circuit board traces and the attached cable harness. It is thus a requirement that operational amplifiers are EMI hardened, as EMI signals, for example at the input nodes, can easily introduce a so-called EMI-induced offset at the output of the operational amplifier. There exist three design measures to reduce the EMI-induced offset. First, one should filter the EMI signal before it enters the input stage. Second, one should linearize the input stage. And third, one should compensate the EMI signal within the differential input stage. Based on these three concepts, designers usually try to improve the input structures of the operational amplifiers during the IC design phase. Here, not only the design itself, but also the influence of layered parasitics need to be considered. We already investigated the influences of such parasitics on folded cascode input stages based on filtering and linearization concepts. In this work, however, we extend these investigations for the compensation concept.
For our investigations, we are starting with a simple folded cascode amplifier. We designed this amplifier to have a differential mode gain of about 80 dB and a gain bandwidth product of about 10 MHz. All circuits are implemented in a 0.35 micrometer CMOS annual technology. The input stage of this simple folded cascode amplifier does not feature any improvements in terms of EMI. Therefore, we replace this simple input structure by other, more EMI-robust input structures. In our research, we use the suggested order of measures to mitigate EMI. These measures are filtering, linearization, and compensation. However, in this work, we only focus on compensation concepts. For more information on the filtering and linearization concepts, please have a look at our previous publications. We will label the reference structure as A and use the designators F, G and H for the compensation structures. In the compensation concept, we try to compensate disturbances that already happened due to EMI. This means that offsets introduced due to nonlinear distortion are counteracted in a subsequent stage. Within this compensation concept, we therefore investigate three different principles: cross-coupled differential pairs, complementary differential pairs, and source buffering. For the cross-coupled differential pair, we extend the reference structure A by a second equally sized differential pair. However, this differential pair is inversely connected, cross-coupled, as shown in structure F. By this means, it's able to compensate current offsets that are introduced by distortions on the first differential pair. By adding a high-pass filter, we ensure that the second differential pair is only triggered at frequencies above the gain bandwidth product of the amplifier. At frequencies below the gain bandwidth product, it simply injects a DC current to the folded cascode output stage. The complementary double differential pair takes a similar approach. It compensates the introduced current offset in the output stage with a complementary differential pair using NMOS transistors, as shown in structure G. The second differential pair is designed in such a way that it creates currents of the same size but of opposite direction, and it therefore compensates the current offset. Due to a high-pass filter, this compensation mechanism is again only active at frequencies above the gain bandwidth product. Source buffering introduces a second PMOS differential pair with the same dimensions again. However, the common source node of the second differential pair is connected to the bulk terminal of the first differential pair, as shown in structure H. By this means, we are able to exploit the backgate effect. By proper dimensioning of the capacitances CH, we force the common mode transfer function of the input pair to 0. The disadvantage with this approach is the need for a capacitance CH that is accurate with regard to absolute values. This is very hard to achieve in integrated circuits. Furthermore, this principle can only be applied for input pair transistors where the bulk terminal is isolated from the substrate. Manufacturing a circuit brings up different parasitic components. These components are obtained by RC extraction. Among others, this includes capacitances to substrate, intermetal capacitances, path and gate resistors. Especially parasitic capacitances play an important role in EMI considerations, as high-frequency signals might be induced into other nodes. We can even see that there might exist a non-neglectable capacitance from the input pins, so the transistor gate, to the output pins, the metal lines on the right side. Furthermore, substrate coupling can also occur, but we will investigate substrate coupling on these structures in detail in a separate work. We try to lay out all structures as similar as possible. All transistors that need to be matched are placed in terms of a common centroid approach. Furthermore, we split all input pair transistors into equally sized unit transistors to ensure best comparability. Structure A therefore serves as a reference for all other structures. The output stage and the biasing blocks are also reused for all structures. However, minor changes have to be made to the output stage for structure G. All of these measures ensure that we can focus mainly on the influences of the different input structures. Additionally, we also investigate the difference when using ideal biasing blocks and the impact of analog I/O pads.
Let us now continue with the performed simulations and the results that we obtained. First, we check whether our amplifier structures meet the specifications of a gain bandwidth product of about 10 MHz and a differential mode gain of about 80 dB. Additionally, we simulate other important amplifier parameters that can be seen here, both for schematic and layout back extracted versions. You can see that all structures approximately meet the necessary specifications. The parameters are color-coded, green meaning good results and red meaning results that might require further attention. For simulating the EMI-induced offset voltage, we configure the amplifier as voltage follower with a DC input voltage of half of the supply voltage. On top of that input voltage, we superpose a sinusoidal disturbance. Finally, we obtain the change in DC output voltage by averaging the output voltage. This offset voltage is referred to as EMI-induced offset voltage. For our first EMI investigations, we use an EMI amplitude of about 500 mV and sweep the frequency from 1 MHz to 10 GHz. This results in this plot. You can see that the schematic and layout back extracted versions behave similarly. The difference in EMI-induced offset voltage between schematic and layout back extracted level is quite low. There is only a small shift in frequency when the highest EMI-induced offset is reached. Furthermore, we can see that there are only minor differences between real and ideal biasing. Altogether, structure H using the source buffering concept shows the best results for this analysis. The changing sign of the EMI-induced offset voltages can be explained due to the phase shift at the amplifier input stage's drain terminals of 180 degrees. This change in sign is happening for frequencies higher than the second pole, which lies at about 5.5 MHz. For better comparability, we calculated the EMIRR for an amplitude of 100 mV and at common frequencies that are used by communication applications. Again, structure H using the source buffering concept performs best, whereas structure A performs worst regarding EMI robustness. The results regarding EMIRR show that no clear trend due to the transition from schematic to layout back extracted level can be observed. To give an example, the EMIRR for an amplitude of 100 mV at the frequency of 2.4 GHz is much better at the schematic level compared to the layout back extracted level at structure G, but structure H shows exactly the opposite behavior.
With that, we have shown that parasitics introduced by layout back extraction can influence the performance of operational amplifiers. An important finding, however, is that the parasitics of the layout do not significantly affect performance when EMI is applied to the input of an amplifier. The amplitude of the EMI-induced offset remains almost the same, however, it is slightly shifted towards lower EMI frequencies. By this means, future EMI-robust IC designs should be eased by knowing that layouting poses no significant influence on the EMI behavior. With these conclusions, we have not yet reached the end of the line. The overall objective is to manufacture all of these investigated structures embedded into an operational amplifier test chip to conduct the same measurements on chip level. Finally, the overall comparison of the EMI performance on the schematic level, layout level and the manufactured IC will be published. I'm Dominik.
And I'm Niki.
We hope you have enjoyed our presentation today.
But anyway, thanks for watching.